Okay, you are not supposed to be seeing that screen. You are supposed to be seeing this screen. Much better. Okay. So the last thing we spoke about in the previous lecture was three-dimensional analysis. We looked at work equals F.dr. Then we looked at work as when our force is a continuous function and how we do it using an integration approach. And finally, we said that okay, if it's three-dimensional, then we do it once for each time. So fx dx, fy dy, and fz dz. Now, we start today by looking at this PIQ. Okay. A 12,500 kilogram truck is accelerated from rest by a net force shown in the graph. Use the work energy theorem to determine the approximate speed of the truck when the force is removed. Knowing that work is equal to force dot distance, what is it that we can do? How can we solve this problem? Take a couple of minutes. So you will find this under PIQs number 15 in today's lecture. 33 people so far who have connected. '71 people connected so far. I'll give you a minute to try and figure out what the correct answer is, and then we go through it together. Okay, let's see how the answers are going so far. Only 20 people have responded. What's going on? Are you asleep?
مستر ما ظهر الصوت.
Refresh the page. Okay. Well done. But 45 people out of 92 respondents have answered it correctly. Now, indeed, what we do is f dot t. Now, given that our equation is f dot d or f dx, and that we have a graph that is given by force on the y-axis and x in the x-axis, the easiest way to find the work done is not to do integration, but to look at the area underneath the graph. Okay, so area underneath the graph is the work done, which is equal to the kinetic energy gained. So 150 times 13 kilonewtons divided by 2 half 12,500 v squared gives me a v of 12.48 meters per second, which is approximately 12.5 meters per second to 3 significant figures. Now, there is something that we keep doing over and over again without formally defining it. We keep saying, okay, this much work is equal to this much energy, is equal to this much kinetic energy, and it's equal to this much spring work. What are we doing here when we're equating all of these works? What is happening when this work is being done?
We move subject.
Change
What
from
subject?
form to form.
So what's happening is we are describing the transfer of energy using the concept of work from either one object to another or from one form to another. Okay. We'll come back to this in a few slides' time, but keep it in mind. Okay. Now, in the previous lecture, we mentioned that if I have a function, I simply input it into the integration, integrate it, and well, I end up with the work done. Now, sample problem 7.08 in your book is quite nice. We have a force which is 3x squared newtons in the I direction plus 4 newtons in the j direction. So this is a two-dimensional force in the xy axis or ij directions. And it is not a constant force, it is a variable force. How much work is done on the particle as it moves from the coordinates 2, 3 to 3, 0? And does the speed of the particle increase, decrease, or remain the same? Right. we have our equation. We put it in. Yeah. We end up with two integrations. We don't have a z من الأساس here, so we don't care about z. fx dx is 3x squared dx. fy dy is just 4 dy. So our x, so our x here, our y is here. Coordinates are always in the xy format. So we go x initial, x final. Sorry, that was a bad thing I just did. From x initial to x final, y initial to y final. And we do the integration. We end up with 3x squared dx plus 4 dy from 2 to 3 and from 3 to 0. We end up with 3x cubed over 3 plus 4y over the limits. And what we end up with is a simple number, 7 joules, which is consistent with what we have been saying so far. You know, work is a scalar. It's an energy it's a form of energy, of transference of energy. So it's just a scalar. We don't have a direction, just a number and a unit. So 7 joules makes sense. Now, if the work done is plus 7 joules, what happens to the speed of the particle? Does it increase, decrease, or remain the same?
Increase.
It increases, right? We're giving it extra energy. So energy more equals velocity more. Good. Now we come to the concept of power. Something we hear over and over again and we use on a daily life basis. But what is power in terms of physics? Just like we define work in terms of physics, you know, we have to define power in terms of physics. So power is the time rate at which a force does work. If a force does W work in a time delta t, then the average power due to the force is what? Then the average power is W over delta t. Rate at which a force does work. So work divided by time. We get the average power. If our average power is W over delta t, what is our instantaneous power? نايمين ما في شكلكم بطارياتكم كلها منتهية على الآخر. The instantaneous power will be dW by dt. Okay. What is the unit of power? The unit of power, what is this thing? What's happening? The unit of power is 1 watt. 1 watt is 1 joule per second. Also, in American, that is 0.738 feet pounds per second, but we don't really use American units. Now, if you're a car fan, you will know a different unit of power. How is the power of a car usually described? When you want
Horsepower.
Horsepower, excellent. Horsepower, 1 HP. which was defined a long time ago as 550 feet pounds per second, which is 746 watts. Okay. Now, someone might be thinking, horses are quite powerful. They can do more than 746 watts of power. You know, have you ever seen a horse kick someone? That is way more than 746 watts. Yes, but when the definition of a horsepower was made a long time ago, they didn't look at the instantaneous power of a horse and define it as the horsepower. It was more like, you know, how much work can a horse do throughout an entire day? Standardized to about 24 hours. Then we have another unit, kilowatt hour. What is kilowatt hour? Kilowatt hour is a unit of power as well. Okay. And it means it's about 3.6 megajoules of energy spent in that 1 hour. Now, if you have been following the news, or if your parents have been hammering on your head lately that, you know, فاتورة الكهرباء جالسة ترتفع وتعريفة الكهرباء ازدادت, we need to, you know, shut off the lights and the ACs when you leave the room so that, you know, our electricity bill doesn't come to a crazy 500 riyals, you would know what a kilowatt hour is. It's the unit by which we measure electricity consumption or energy consumption. How do we solve for instantaneous power using the definition of work? Well, power is dW by dt. We know work is F cosine theta, so that's just F cosine theta dx by dt. F and cosine theta are constants. We take it out. We end up with dx over dt. What is dx over dt?
Velocity.
Excellent. Velocity. So power is Fv cosine theta. Work is Fd cosine theta. Power is Fv cosine theta. Any questions so far?
Doctor,
Yeah.
this section 7.6 is not in the work plan.
How is it not in the work plan? Interesting. Seems I have made a mistake. Okay, thank you for informing me of this, because this means I have to fix it in the work plan later today and repost the work plan. Thank you for pointing it out to me. I made a mistake. It should be there. I'll actually upload an updated work plan today, because we are obviously, you know, behind of compared to the initial work plan that we had. So I'll upload a revised one today showing the latest updates. Okay. Any other questions on this so far?
No, it's clear.
Okay. Then in that case, don't want this. Go away. Let's see if we have actually understood this. So I'll start the next PIQ and make sure you rewind, reload if it's not working. Engine A has a greater power than engine B. Which of the following is correct? Engine A and B can do the same work, but engine A can do it more quickly. Engine A and B can do the same work in the same amount of time, or engine B can do the more work than engine A in the same amount of time.
Doctor?
We don't have the same question.
Yeah, we don't have the same question.
طالع سؤال غير دكتور.
لا حول ولا قوة إلا بالله العلي العظيم. Moodle is enjoying making me miserable these days. There we go. Now it should be okay. It should show you the correct question. Okay, let's take a look. This was a landslide by a big margin. So these are our results. So many people have chosen the correct option that it's just beautiful to watch. Of course, the correct answer is engines A and B can do the same amount of work, but engine A can do it more quickly. Because the definition of power is work over time. So if something has greater power, then it can do the same amount of work more quickly. There's nothing stopping you from doing the same amount of work. It's just how quickly you can do it. If I can collect 20 books per minute and you can collect 50 books per minute, there's no problem with both of us getting 100 books. Only that I'm going to take 5 minutes to collect them and you're just going to take 2 minutes. So you have a higher power of book collection than I do. Okay, I can do the same amount of work, 100 books. It's just going to take me longer to do it. So while we sleep, our body is using an energy at about a rate of 77 watts. How many food calories do we use during an 8-hour period? We can assume that a calorie is about 4186 joules. Slow and steady wins the race. Okay, answers are pouring in. Okay. Excellent. Pretty much everyone got the correct answer. We're using energy at a rate of 77 watts, which is 77 joules per second, which means for an 8-hour period, I have 3,600 seconds in each hour, 77 joules per second each second I am using. And then I want to convert it to joules, so I will divide by 4186, and I end up with 529.77, which is 530 calories joules per second. Sorry, to 3SF. Now, I have a question for you. How many of you have ever taken a can of beverage, can of Coke or something, and taken a look at how many calories it has?
Coca-Cola Zero, doctor, doesn't have any calories.
So apparently Coke Zero does not have any calories whatsoever, right? So we are So the reason Coke Zero does not have any calories is because it really almost has nothing of value in it. Anything of value is bound to have some form of, calories. The fact that there is no calories in it means, in advance that it's absolutely useless. Okay. But let me open something. I want to show you something. 1 minute. Trying to find it. Give me a minute. I have an idea. Ha! They have actually fixed it. So it used to be that whenever you look at a can of Coke, for example, it would give you the number of calories and it would give you the number of joules. And I am trying to find one where it shows us both joules and calories. Okay, here we go. Now, how many joules of energy are in this can of Coke? Remember this. So how many joules of energy?
83,702. 837,000.
837,000, give or take, right? Joules. So that's 837 kilojoules. But then there's a problem. Okay. 837 joules is not a lot of energy. 837,000 joules is not a lot of energy, is it? I mean, it can be expended quite quickly. So why do we become fat when we drink a lot of these? There seems to be a mismatch between how many calories are written and how many joules does it, correspond to. Anyone goes to a gym and has a Fitbit or, one of those Galaxy watches or, the MyZones that calculate how many calories you burn while you're on the treadmill or on the bike or doing weightlifting or whatever? If you've ever done one of these, you will notice that pretty much a full hour of working out, okay, combination of aerobics, HIIT, bit of weightlifting, warm-ups, would, you know, burn somewhere between 600 to, you know, somewhere between 600 to, if you're really, really working hard, training hard, about 1,000 calories. And I personally have many a time started wondering, so why is it this mismatch? There is no way that this one bottle, okay, is actually equal to this much amount of work. Turns out there is a bit of cheating going on. So they have written here calories, right? 200 calories. In reality, this is not 200 calories. This is 200 kilocalories. So it's not 200 calories, it's 200,000 calories. Scientifically speaking, when we are dealing with our units, this is not 200 calories where each calorie is 4186 joules. No, this is 200 kilocalories where 1 calorie is 4186,000 joules. Okay, in the food industry, they usually don't trust people enough to trust them with, you know, with a unit such as kilocalorie. So they just tried calorie. عادي اصلا وين تفرق؟ كالوري كيلو كالوري كلها واحد. المهم في كالوري في الاسم. تو مين بيسأل؟ Okay, so if you have ever wondered why on earth there seems to be a mismatch, or if you look at some stuff where they give you in terms of joules and in terms of calories, okay, and you see you multiply by 4186 and you're like, okay, this does not make sense, these numbers don't match. This is the reason. You need to multiply it by 1000 and then suddenly everything is going to match. Okay, and also, you know, this is how they get you to eat without feeling so guilty, or at least get me to eat without feeling so guilty, which is why I'm so fat. Okay. So this is what I went to bring from the kitchen here. Please tell me I can focus enough. Focus. There we go. And it's mirror imaged. Please tell me you can see it properly. Not mirror imaged. Focus. Focus. Okay, can anyone read the second line?
506.
568 kilocalories. So, you know, at least Pufak Oman ما جالسين ينصبوا علينا, they have written kilocalories, which actually puts them in a lot of disadvantage in the market, because, you know, when you see that Pufak is 568 kilocalories and everyone else just writes 200 calories, it gives you the indication that, you know, it gives you the indication that it's better to have a can of Coke or a bottle of Coke rather than have a pack of Pufak. Now, it turns out, yeah, a whole bag of Pufak is about 12 grams. So that bag of Pufak is basically going to give you about 68 kilocalories, while that can of Coke is going to give you 200,000 or 200 kilocalories. ما حصلت تراني كميشن من بوفك عمان, ها؟ Fair notice. Okay.
Okay, but when you work out, do you burn kilocalories or calories?
So when you work it out, you need to put it in calories, in terms of calories, not kilocalories.
No, but you said 600 calories per hour, right?
So yeah, so that's 600 kilocalories again.
Okay.
Okay. In terms of joules, so usually, if I'm confused, I transfer it to joules, and that makes a bit more sense to me.
Okay.
Yeah. Someone was asking something? حد كان يسأل شيء؟ No? Okay. سوينا دعاية حق منتجات عمانية. هذا الفيديو بعدين بيروح على يوتيوب. You know, we're doing marketing for Omani products. Our economy needs it. Okay. Now we've been doing something all over, and I mentioned it a little bit ago that we're going to talk about it. You know, that whole thing of, you know, transferring energy and work taking energy from here and putting it here. اوكي كان المفروض نجيب شيبس عمان. بوفك شويه معروف اقل، شيبس عمان مشهور اكثر. So I'll tell you something about chips Oman because I'll never forget the story. I lived in London for 10 years of my life. وكنت اودي معاي شيبس عمان، وانا كل ما اجي اجازه عمان اخذ معاي كرتونين واوديهم. شنطتي فاضيه، ملابسي كلها هناك، اغراضي كلها هناك، اودي معاي. الحين مره خاطري في سندويتش جبن وشيبس وماشي شيبس مخلص، صار لي فوق السنه ما راجع عمان. قمت ادور، لقيت دكان يبيعه. تخيلوا الكيسه الواحده يبيعوها بكم؟ اتكلم الكيسه الواحده هذه اللي كانت في يدي الحين، ها، كيسه واحده يبيعوها ب 750 بيسه. قلت لهم غربل الله بليسكم، اجيب لكم انا كرتونه كامله واعطوني نص الارباح. قام الرجال عاد ذاك يقنعني this is good quality product we are bringing it from عمان. قلت له عرفت تراني اجيبه معي كرتونين كل كم شهر ببيع لك اياهم. زين. شيبس عمان كان باوند ونص او باوندين، والبوفك كان بعد تقريبا نفس السعر. ما كان عندنا وقت، الدكتوراه ما خلت لنا وقت. شريتها، الله والله شريتها، كان خاطري فيها، صار لي ومخلص الستوك عندي من زمان. شريت لي كيستين وقمت اتلذذ كذاك بالقطع، بالحبه الحبه كذاك، ما اكلهم ورا بعض، بالحبه كذاك، خلي الطعم يلصق في الفم. Okay, so W equals delta K. We have been using now this equation for 2 lectures, 3 lectures, give or take. Now, we have been talking about work, and we have been talking about, you know, more energy, positive work, less energy, lost energy, negative work. So we have been dealing with something, we have been saying something without actually, you know, defining it. It seems that work is how we say, you know, we put energy into the system or we take energy out of the system. Okay, fair enough. Now we spoke about multiple energies so far. We spoke about energy related to gravity. We spoke about energies related to springs. The gravity one, we called it gravitational potential energy. The spring one, we call it elastic potential energy. We also spoke about losing energy due to friction. So as thermal energy or as heat. And on the other side, you know, we said equals delta K, where K is the kinetic energy. Now, what are we doing here? Just look at the slide and what are we saying here really? We're saying that whenever we say something's undergoing work, so whenever something is gaining extra energy or losing some energy, okay, the kinetic energy changes. Okay, could it be, for example, that W is not equal to delta K, W is equal to something else? ممكن ولا ما ممكن؟
Yes.
So can I have, for example, the positive energy gained from the gravitational potential energy goes to the elastic potential energy of the spring, والkinetic energy ما يتغير. Is that possible?
Yes, you can.
That's okay, right? There's no problem with that. Actually, we have done sample problems before in which we did exactly that. Right? Okay. Going to okay. This thing is okay. Here we have this fancy guy. Have you ever seen bungee jumping? Do you know what bungee jumping is?
Yes.
Yeah, one person knows it. Have you tried it? I want to try, but I'm too scared.
No, I don't like this actually.
No? Anyone here ever tried bungee jumping? So
ايوه بس بدون حبل.
هذا صار انتحار ما صار bungee jumping.
I went there, but I was too scared, and then I went back.
في الماء دكتور في الماء.
Yeah, that sounds familiar. I have gone so many times that I have never actually done it. Okay, so in case you don't know what bungee jumping is, كلنا نعرف كوب الشاي كيف نسوي. أنا دائما أرجع للشاي. شوفوا دائما أمثلتي لها علاقة بالشاي. الحب الأزلي. إنزين. شايفين كيف هذيك التي باج مال ليبتون نمسكها من الورقة وندخلها في الماء ونطلعها. إنزين. This is exactly what bungee jumping is, but instead of the tea bag, it's you. So they put your waist or usually your feet, okay, with an elastic rope, and you jump out of a really, really, really high place. Okay, and you end up just, well, you end up like a tea bag. Okay. Let me show you, because seeing it is different than, you know, explaining it. And this also means that later on, okay. Oh, there we go. This one looks fun. The last one. No. You stay silent. Okay, so this is what bungee jumping is. So you go all the way up a very, very high building. Look how high you are. And then they tie you up with an elastic rope, and the rope has to be elastic. Okay. And then you need to be crazy enough to do this. Whee! Okay. Look, literally going up and down. And yeah. Okay, so this is what bungee jumping is, and there's actually a lot of physics going on in one of these. Okay, so first thing first, let's describe a few of the energies that we already know, formalize them, and then go into, you know, the details. Potential energy, some energies are potential. This is the energy that can be associated with the position of the object in a system that exert forces on one another. So a system of objects, for example, might be Earth and a bungee jumper. Okay. So you have an energy just because of your position. Or for example, spring. Just because the spring مشدود, okay, it's elongated, it has an energy stored. Okay. So this guy forgot the rope. So I would suggest you don't forget the rope when you do something like this. This is probably not a very good idea. Okay. This guy is having a lot of fun. So that's potential energy. What other types of energy we have? So far, we have looked at three types of energy: gravitational potential, elastic potential, and what else? What's the third type of energy that we've been looking at?
Air potential.
We had friction, but that was a force.
Gravity.
We said gravitational potential energy, yes. So we had the gravitational potential, the elastic potential that has to do with elastic bands and springs. We had the equal delta K everywhere, right? So the kinetic energy. Now, kinetic energy is not potential. It has nothing to do with your position. It has to do with your movement. So that's a different type of energy, which we will come back to. Now, potential energy. Now, whenever something goes up, say I throw an apple, okay? While it is going up, there is work done by gravity on it. This is why it slows down. Assuming no air friction, this is why it slows down. On the other hand, eventually when it reaches at the very top and starts coming back down again, it increases its velocity, and there's also being work done on it. So we have here gravitational potential energy, UG, okay? And the change in it can be positive or can be negative. If we start with a high energy, I'm throwing an apple, I start with the high energy, by the time it reaches the top, it will have a low energy. It would have lost energy. Where did that energy go? I started it off with kinetic energy, 100 joules. I threw the apple up. Eventually, at the very top, it stops and then starts falling down again, but for momentarily, it stops. Why does it stop? Where did that energy go?
Potential energy.
It transferred to gravitational potential energy. Yeah. To be able to go against gravity, you are doing work against gravity and gaining that as potential energy. Okay. Now, I don't have these programmed into Moodle yet, so we'll just do them over the chat screen. Okay. Say an apple of mass 100 gram is raised through a vertical distance of 1 meter. What is the work done by gravity on the apple? And what is the change in its potential energy, delta U? Now, be careful, because our work is mg, distance, and then cosine theta. So think whether you are going with the direction, is your theta 0 or is your theta 180? Going up, you're going against the work, against the force, so it's 180 degrees. Going down, you're parallel with, so it's 0 degrees. I'll give you a minute. Put it into, write it down in the chat screen. What do you think the answer is? Why is no one typing anything in the chat screen? Nimtu? I'll give you a minute to think about it. Okay. So we have so many C's. المفروض C إنها تكون يعني زين. So many C's, a few D's. So we are starting here, and the apple is going here. What is the work done by gravity? F dot D mg distance cosine theta mg distance is 1, theta is 180 degrees, so you end up with minus mg, which is equal to minus 0.1 g. If this is correct, then my final energy here will be what? If I start with 0 and I go through minus 0.1 g, this will be minus 0.98 joules. I will end up here with I will end up here with 0.98 joules of gravitational potential energy. So either C or D can be right, depending on whether you choose G to be positive upwards or downwards. Okay. Your work is going to be minus 0.1 G. If you take G downwards to be 9.8, then it will be minus 0.98 joules. So your answer would be C. If you take downwards to be negative, minus 9.8, you will end up with minus minus. So your work will be 0.98 and your delta U will be minus 0.98. Now I'll show you some magic. You like magic? Let me show you some magic. I will calculate for you the work done or the change in potential energy when I am moving a suitcase along different paths. By moving straight up, if I take this bag and go straight up, my work is mgd cosine 180, which is my height, I would call it h, so that cosine 180 is minus, so I end up with minus mgh. So far, so good. أي اعتراضات؟ Okay. Now I am going to take the same bag up the same height, but on an inclined surface, moving a longer distance. Okay. What is the work going to be? Same, different, less, more?
The same, mgh.
By moving along the inclined plane, it's still f dot d. So it's mg d cosine theta, cosine alpha, where alpha is the angle between the direction of my force, which is down here, and the direction of motion here. So it's this whole thing alpha, 90 plus theta. Cosine 90 plus any angle is the same as saying sine of that angle. And I end up with exactly the same, minus mgh. Which means physics is being for once nice to us because we can be lazy. It doesn't matter what path the object takes, we always take the easiest path to calculate, to do the calculation on. The change in potential energy only depends on the vertical height h with respect to the reference level. So mgh is, we look at the final potential energy and the initial potential energy. What happens if I start here, I go this way, this way, this way, this way, come back, أدور في الحوش شوية، أروح بيت الجيران وبعدين أجيب هنا. What is my change in potential energy?
The same.
It's still the same. Remember our example of how your mother wants you to do things her way? It doesn't matter what other things you do. This is coming back to us again now. Okay, it doesn't matter what the path is, we get, for gravitational potential energy, we get the same result. Now, this is an example of what we call a conservative force. If the work done by a force in a system is independent, so it does not matter, of the path taken, then we call it a conservative force. And in a conservative force, if you start at one point, go all around Earth and come back at the same point, you would have done zero change in work. Okay, so W1, I'm going from A to B. My change is UB minus UA. MGH مثلا. Then I come back from B to A, but along a different path, not the same path. My work will be exactly minus W1. So my net is going to be 0. Now, it's important to understand this is not true for all forces, okay? This is only true for a specific subsection of forces, which we call conservative forces. Questions? Let me take a quick look at something. Okay. Let's call this a day. And then at the beginning of next lecture, we will start with this PIQ and move on from there to finish 8.1, 8.2, and 8.3. And I think it's better to finish them all in one lecture so that you are actually able to follow through all in one go. We're going to have a lot of fun going on slides at some point.